Welcome to this explainer. We're jumping right into a really fascinating physiological puzzle today. We absolutely take breathing for granted, right? Air goes in, air goes out. But what if I told you a pretty significant chunk of the air you just breathed in was completely wasted? Like it didn't help oxygenate your blood at all. Today we're going to decode this entire idea of dead space measurement. We're talking about the brilliant minds who figured out how to measure the seemingly unmeasurable. We'll break down the Bohr equation and physiological dead space, look at the Enghoff modification, and finally map out both anatomical and alveolar dead space.
So, here is our roadmap for today. 1. The wasted breath problem. 2. Bohr and physiological space. 3. Enghoff's arterial modification. 4. Fowler's anatomical dead space. And 5. Calculating alveolar dead space.
Okay, Section 1, the wasted breath problem. Let's get our bearings and establish the core hurdle here before we even touch the math.
Just to make sure we're completely aligned, we really need to nail down what we mean by wasted air, or dead space. Basically, when you take a breath, your tidal volume, some of that gas never actually makes it to your alveoli. It just gets stuck in the conducting airways. Your trachea, your bronchi. And because there is literally zero gas exchange happening in those tubes, that specific fraction of your breath is exactly like completely unchanged atmospheric air. It just sits there, taking up space.
Picture your tidal breath as this perfectly solid block of air. We can take that block and sharply slice it into two distinct pieces. One slice is that unchanged atmospheric air, the dead space. The other slice is the exhaled alveolar gas, which is packed with carbon dioxide because it actually did its job and participated in gas exchange. So to measure dead space, we have to find a way to single out that first slice, operating under the assumption that it contributes absolutely zero CO2 to your exhaled breath.
Moving to Section 2, Bohr and physiological space. Time to look at our largest Matryoshka doll, the total physiological dead space, and the guy who first tried to quantify it.
Let's rewind way back to 1891. A physiologist named Christian Bohr published a paper on lung respiration. Now, fun fact, Bohr actually wanted to determine alveolar CO2, and he was basing his anatomical dead space estimates on the measured volume of conducting airways in cadavers. He never actually intended for his equation to be flipped around to calculate dead space, but, well, that's exactly what we do today. The Bohr equation looks at the ratio of dead space volume to tidal volume. It uses the difference between the fraction of CO2 in the alveoli, that's the FaCO2, and the fraction of CO2 in your mixed expired gas, the FeCO2. By comparing what's in the alveoli to what actually makes it out in the exhale, you can calculate the total Bohr dead space.
But wait, here is a massive roadblock. How in the world do you measure alveolar CO2 in a living, breathing patient? You see, regional alveolar CO2 varies wildly across different areas of the lung, mainly because of ventilation-perfusion ratios. Think about it. Even in a totally healthy person who's just standing up, the partial pressure of CO2 at the apex, the top of the lung, might be around 28 millimeters of mercury. But down at the base, it's 42. So you can't just magically pick one single number to plug into Bohr's perfect equation.
Which brings us to Section 3, Enghoff's arterial modification. Let's see how this roadblock turns into a clinical tool, thanks to a clever tweak that went totally unrecognized for over a decade.
This is such a brilliant illustration of theoretical perfection clashing with clinical reality. So in 1938, Henrik Enghoff proposed a much more pragmatic workaround to Bohr's impossible variable. Since finding an average alveolar CO2 is basically impossible in living subjects, and don't even get me started on patients with lung disease, Enghoff just substituted it with arterial CO2, or PaCO2. His logic was super sound. Arterial blood is the mixed product of all your lung units combined, so theoretically the CO2 level in your arteries should represent the average CO2 of all those alveoli put together. You just draw arterial blood, grab the CO2 level, and plug it right in.
Now there is a slight catch here. Because arterial CO2 is generally higher than alveolar CO2, the number you get from the Enghoff equation is slightly larger than the proper Bohr physiological dead space. Enghoff's measurement is catching more than just pure dead space volume. It actually gets increased by any physiological mismatch that creates a gap between arterial and alveolar CO2. We're talking things like intrapulmonary shunts, diffusion impairments, and VQ heterogeneity, where the blood flow and the airflow just aren't matching up properly.
And because it includes all those extra variables, the Enghoff modification can't really tell you the exact cause of that CO2 gap. But I literally love this quirky phrase from the source material. It acts as a highly sensitive detector of non-specific lung badness. ICU doctors rely on this heavily, because even if it doesn't tell you exactly what anatomical structure is failing, it acts as a giant flashing warning light that something is severely compromising the efficiency of the patient's lungs.
As the text playfully puts it, it's good enough for government work. And why is that? Well, most patients in the ICU don't have some massive 50% intrapulmonary shunt that's throwing the numbers into total chaos. It's so incredibly useful clinically that the Enghoff modification has essentially become the de facto definition of physiological dead space that you'll find in most medical textbooks today.
Section 4. Fowler's Anatomical Dead Space. So we've got our total physiological dead space, right? Now we need to pop open the next Matryoshka doll and measure just the purely physical conducting airways.
Enter Ward Fowler. In the late 1940s, highly sensitive nitrogen sensors hit the scene. Fowler realized he could use this brand new tech to physically measure anatomical dead space in a living person, completely ditching the need to rely on cadavers like Bohr did decades prior. He came up with a technique called the nitrogen washout.
Here's how this wonderfully elegant procedure actually works. First, they hook the patient up to a pneumatachograph, which measures flow over time to give us volume, along with a nitrogen sensor. Now, normal room air is roughly 79% nitrogen. The patient takes one single massive breath of 100% pure oxygen. That pure oxygen completely floods the respiratory tract and flushes out all the nitrogen sitting in the anatomical dead space. Then, the patient exhales, and we graph the nitrogen concentration against the exhaled volume.
As they exhale, Fowler noticed these highly distinct phases that basically narrate a physical story of where the air is coming from. Phase I is the very first waft of gas. Because this air was just chilling in the dead space, it's pure oxygen, zero nitrogen. Then we hit the middle phase, which is a rapid upslope in nitrogen. This happens super fast as the pure oxygen in the airways mixes with the nitrogen-heavy gas coming up from the deep alveoli. Finally, we reach Phase 3, a stable, nitrogen-rich plateau. This means we are now completely emptying out the gas-exchanging alveoli.
To find the actual volume of the anatomical dead space, Fowler had to pinpoint the precise cutoff on that rapid middle upslope, the exact boundary between dead space and alveolar gas. And how did he do this before modern computers? Get this, he estimated visually with the help of a squared transparent ruler. He literally just looked at the paper graph and compared the areas above and below the curve to find the midpoint. And the crazy part? He validated it by building fake rubber dead spaces of known volumes, proving his transparent ruler method was shockingly accurate.
Section 5. Calculating alveolar dead space. It is time to open our final Matryoshka doll and track down that hidden alveolar dead space.
Bringing it all together now, we've got our total physiological dead space from the Bohr-Enghoff equation. We've got our physical, anatomical dead space from Fowler's nitrogen washout. So how do we find the alveolar dead space? Those specific alveoli that are getting plenty of air but no blood flow. We literally just do the math. We take Enghoff's total physiological space and subtract Fowler's anatomical space. The remainder is our alveolar dead space. We have to deduce it this way because, right now, a direct measurement technique that zeroes in only on the alveolar dead space is completely elusive to medical science.
Which leaves us with a pretty big question. We have spent over a century stacking equations, from Bohr to Enghoff to Fowler, just to deduce what's happening deep inside our lungs. But since direct measurement is still elusive, what future technologies might finally let us map these non-perfused alveoli in real time? Are we waiting on advanced real-time volumetric capnography? Or maybe some totally wild imaging modality that hasn't even been invented yet? It's an absolutely thrilling frontier in respiratory medicine. Thank you so much for joining me for this explainer on decoding dead space. And hey, keep wondering about that breath you just took.